everybody hear me? Good morning. It's great to see everybody, or at least sort of. And I'd like to set this up by talking about our commercial market outlook. So our team has the exciting job 24/7, 365 of looking at the commercial aviation market, obviously specifically the addressable aviation market for our company, but not only what's happening today, but how that informs the future of commercial aviation. What that means in terms of production rates, what that means in terms of the growth of commercial aviation, what are the key drivers. So everything from the economic factors and the fundamentals that drive aviation to what the industry could need in the future that we need to think about today to be ready for in the long term. And I know some of the team or some of the group, the panel that will follow me, might even talk about applications beyond what we're looking at, but it's all part of that commercial aviation ecosystem, the part that has connected the world for over 100 years and is so closely tied to the global economy. In fact, I would say the backbone of global transportation is de facto now commercial aviation, and so it's an exciting industry to be part of. I'd also like to start by saying we've been doing this a long time. Our commercial market outlook, which used to be called the current market outlook, we've been doing it since 1961. Every single year we've published a forecast. And I guess some people could ask, why do you publish one every year? And the reason is our assumptions, our drivers, our fundamentals could change. The industry could change. And the things that we look at obviously are very dynamic. And so we've been doing this for close to 63 years now. But I'd like to look back just 20 years because our commercial outlook is a 20-year projection of commercial jet demand. And in 2004, think about the world in 20 years ago, and maybe some of you weren't in the industry then, but in 2004 it was very dynamic. The US industry was in a huge flux. Post 9/11, low-cost carriers, consolidation of the industry, bankruptcies. It was very, very dynamic. In fact, in 2004, I worked for Delta Airlines before I came to Boeing. And the outlook that Boeing produced in 2004 said, we're expecting the industry between 2004 and 2023 to need about 25,000 commercial deliveries. What happened in the next 20 years was almost exactly as projected, which makes us look like geniuses, but really not. If you think about it, what happened? Well, over the last 3 years, ourselves and our competitors have under-delivered the industry because of the impacts of the pandemic. We had obviously huge supply chain impacts, our own production system impacts, and just resource challenges that resulted in us and Airbus under-delivering the market by at least 2,000 aircraft over the last 2 years. So you could say that we were actually conservative in 2004 in terms of what we projected the industry would need. We also projected the size of the market by various segments, and while we were directionally correct, there was a lot of dynamics that changed over the last 20 years as well. We were close to on target in the wide-body space. We over-forecast by a few hundred aircraft. But we way over forecast the regional jet market. Way over. Think about what was happening in the US in 2004, smaller aircraft, regional connectivity. And what happened over the course of the last 20 years is a shift towards the single-aisle market. So at the top line, we were very, very close, but there are obviously dynamics within that space that have changed over the last 20 years. What drives airplane demand is passenger traffic. Obviously, the cargo space is part of that, but I'm going to focus on passenger traffic. And the interesting thing here as well is in 2004, we almost exactly projected the industry's traffic level in 2023. The way we got there, though, is not exactly how you might obviously expect. We had the global financial crisis in 2008, 2009. We had a period between 2014 and 2019 where the industry actually outgrew long-term trend by 1 or 2 percentage points because of a very favorable market climate, low fuel prices, low interest rates, and the industry actually grew at 6-7% per year, which is quite a bit higher than the long-term trend. But the biggest impact to commercial aviation, obviously the pandemic. However, if you think about how resilient the market has been since then, how fast demand came back, we essentially were back to, at the end of 2023, early this year, where we were in 2019 and now continue back on that long-term trajectory. And I think this is a great demonstration of the value, but also the resilience of air travel and how important it will be going forward as well. It'll help us inform where the market is going, but I think also you can see changing demand patterns. For a while, people would say nobody would ever travel for business again, or corporate travel would never be the same. And while that was true for a while, clearly this year is when it's all coming back. But even within that lull, I would say, in corporate travel, so many people prioritize travel for their own needs, for their own values, and you can see some of the stats here as well. People are traveling a little bit longer, a little bit more, because it's the experiences that drive how they value quality of life in the various parts of the world. That being said, what drives commercial aviation will continue to drive demand, and the fundamentals are strengthening. The global economy is steady and diverse. We've never seen a more diverse, obviously, global economy that will continue to grow around 3% per year in the medium term. Inflation is decelerating, which is good for all of us, but also good for affordability of air travel. And interest rates are falling, which again gets us back to the normal paradigm in terms of how the aviation ecosystem works. So there's a tailwind in terms of the macro fundamentals for air travel demand. Like I said earlier, we look at so many different things, and every year we update our assumptions in terms of our commercial market outlook. But think about all the different things that go into our forecast, and also the fact that every region of the world, every country of the world is unique in terms of the speed of growth. We are one of the most mature aviation markets in the United States, but we're also very large, right? So a small growth rate in the United States is a huge demand driver, especially when you think of replacement opportunities for the existing fleet. While in emerging and developing markets like Southeast Asia, like India, you have a significantly higher growth rate opportunity. A great example of this would be when we think about opportunity going forward. Everybody talks about how India's demand, India's economy is growing the fastest of all the up-and-coming markets. If anybody, maybe some of you follow this as well, but if you know how big the Indian fleet size commercially is relative to the Chinese market, there's 4,000 commercial jets in China, there's 650 in India. So there's a huge opportunity to grow. The growth rates will be higher, but that market base is obviously different. So in many ways, India is 15 years of accelerated growth away from where China is today. So you think about all these different speeds, very diverse. That's where the market, dynamics come into play, and what's interesting for us to follow every single year. I also want to look back, and I think maybe this helps tee up the future panel when we think about where we were 2004, where we were 20 years ago in terms of looking at the market opportunities, and where we might be today looking 20 years in the future. So 20 years ago, we were delivering our 1,500th 737 NG. Today, we've delivered over 1,500 737 MAXs and over 11,000 total 737s in the program's history. We launched the 7E7 Dreamliner, which became the 787, and now we have over 2,000 orders for that aircraft and about 1,100 in service. And then we delivered 20 years ago the 500th 777 jet. Now we're above 2,000 in terms of total demand, and we're launching and bringing into service the 777X family to replace today's 777 over the next 18 months. So fascinating to see how the innovation has changed over the last 20 years and continues to support that demand with new technology aircraft. I also want to talk about the global network because, like I said before, I used to work at Delta. I was a network person. Network drives demand. And it's fascinating to watch how airlines continue to deploy aircraft in so many different ways. The number of airport pairs that are connected today is more than double the number of airport pairs that were connected in 2004. And so now there's about 22,000 city pairs, airport pairs, that are connected with nonstop flights. What's more fascinating potentially for you and for me in the near term is the fact that the same number of airport pairs are connected today than were 5 years ago in 2019. What's more fascinating, I guess that would make sense since traffic's back. What's more fascinating to me is that they're not the same city pairs. They're not the same markets. There are 4,000 airport pairs that are no longer served. There's 4,000 new ones that weren't served in 2019. And I think that demonstrates, again, the versatility of commercial aviation. You can redeploy airplanes a whole lot faster than you can redeploy train tracks or other modes of transportation. And I think that speaks to the versatility, how airline networks can continue to be dynamic to serve the evolving needs of the global economy. Another thing that's fascinating and potentially not news to you, but maybe news to travelers, is that air travel continues to be very, very affordable, and that's another way to continue to increase connectivity globally. You can see three things indexed back to 20 years ago. Air traffic, the CPI, so just overall consumer prices, and then airline yields. And remember, this is nominal airline yields. These are not adjusted for inflation. So you can see the consumer price index has doubled essentially in 20 years, no surprise. The average ticket price today nominally is the same as it was 20 years ago, which is incredible. And this is adjusted for stage length. So on a real basis, tickets are actually close to half price of what they were in 2004, which is another enabler. And I think also it enables that traffic growth you've seen, but it's also brought into the possibility of cheaper air travel is brought to us by evolving aircraft innovation. And so if you look at this chart, and I think the team behind that follows will talk a little bit about the future, but on average, the industry, because of new technology aircraft, because of innovation that airlines have brought into their business models, on average, is improving about 3% per year in terms of fuel burn, in terms of fuel efficiency in the commercial aviation market, in terms of gallons per revenue ton kilometer. So there's a number of things in play there. Airlines have more efficient aircraft, they're flying them more efficiently, they're also flying them more full, so you have more passengers per aircraft per departure. And overall, this is improving the efficiency of the global network. And that's going to continue now that we're back to pre-pandemic levels along that long-term trend. We're delivering more new technology aircraft into the market. Airlines are back to pre-pandemic productivity levels. And going forward, those fundamentals will continue. And in terms of where we are, I want to say this is obviously a little bit of a current situation as opposed to a long-term view, but I want to give you a sense of where we are in the market today. Because of supply chain constraints, because of our own regulatory challenges and other challenges in the marketplace, the industry is somewhat constrained. Airlines would like to have more new airplanes than we've been able to deliver. As a result, the age of the fleet is higher than it used to be because airlines are holding on to aircraft a little longer than they otherwise would. So those things over the next 5 years will get solved. Our supply chain challenges will abate. Our production rates are already increasing. And at the end of the decade, we're going to be back again to that equilibrium where we're seeing new technology, efficient aircraft, replacements, airline retirements and fleet replacements will be back to normal levels. And that pent-up replacement demand will be eased. And we'll be back to that long-term trend, the sustainability improvements that new technology aircraft bring to the market. And just an illustration of what I mean in terms of pent-up retirement demand, on average, and this is fairly consistent through the last 4 decades, on average, every year, about 3% of the global fleet is retired. You can see since the pandemic began, there's been a disruption in supply. So as a result, the average retirement rates are cut in half. Airlines are holding on to aircraft longer. They're waiting for those aircraft, and that's what we're working towards. That's what we're doing in the next few years to help the industry, provide that capacity the industry needs to continue to refleet, to refresh, and ultimately reduce the emissions and improve their fleet efficiency. This is really an illustration of what that means in terms of the average fleet age. So about a year and a half, maybe even close to 2 years per airplane in each of these segments in terms of older average ages relative to what we saw in 2019. The single aisle fleet used to be about 10 years old. Now it's about 11 and a half years old. The wide body fleet is over 11 years old. They're waiting for new technology aircraft a little longer than they otherwise would because of this disruption in production, supply chain, and human resources. But one thing that the industry's been really remarkable, I think, not just over the last 5 years, but over the last 20 years, is productivity. Airlines, because of the new technology aircraft, because of capabilities that aircraft bring, have been able to evolve how they fly, make their fleets more productive, and ultimately deliver that lower cost that the consumers need, that airlines need to grow and be profitable. But I think it's fascinating to look at some of the dynamics here. In the single aisle market, aircraft the size of the 737, on average, the fleet has grown about 3% per year, which is what you kind of expect. Seats have grown almost 5% per year because airlines are taking slightly larger aircraft, and they're taking aircraft with a little bit higher seating density. Maybe not great for passengers, but great for average fares. So over time, airlines with these new technology aircraft are actually able to fly them a little further. So the average stage length is higher, and ultimately, what we're seeing in terms of productivity is, in terms of available seat miles, available seat kilometers, we're seeing almost double the growth that we see in terms relative to the average growth rate of the fleet. So airlines are being more productive by finding ways to fill, finding ways to grow, and finding ways to fly further. On the wide-body side, things are a little different. That's why I say it's kind of a little bit of a meeting in the middle. Single aisles are getting slightly larger. Wide-bodies are getting slightly smaller. The 787 that I talked about earlier, 777 aircraft, mid-sized twin-engine aircraft, and those innovations enabled airlines to go longer distances with the right size, the right capacity, the right economics. And that has actually helped airlines fly to more destinations, connect more city pairs, but the average seat size on a wide-body jet is actually smaller than in terms of growth than you'd expect. And so you can see, again, the dynamics are really optimizing the cost and the capabilities with the route and the demand in the market. And so kind of different dynamics, even though both are driving growth in the marketplace. Going forward, though, this is really kind of an interesting question. I think it's an open question, something that we look at Boeing. When we think about demand in the market, you think about what are the key drivers, but how can airlines fulfill that demand either with larger aircraft, with more aircraft, or how do airlines actually solve it? So over the last 20 years, one thing that we predicted, but really not well enough, is productivity. Over the last 20 years, airlines found ways with yield management, with network planning, with optimization to dramatically increase load factors from the 70s to the over 80% rates, to the point where I think we would mostly agree that there's not a lot more room for airlines to increase load factor above 85, 86% on an annual basis. Airplane utilization is significantly higher than it was 20 years ago. Airplane capabilities, lower maintenance requirements, and ultimately longer stage lengths keep aircraft in the air longer, and there's not as much upside over the next 20 years. Average seats per airplane has grown via, like I said, slightly larger aircraft, but also densification. And there's some opportunity with today's aircraft, but not a dramatic increase expected over the next 20 years. So when we think about the fundamentals that are driving air travel, going forward, there are productivity opportunities, but a lot of that growth is going to have to come from new airplanes. I thought it'd be interesting to think, as we introduce the future, to look back at as well at technology, because again, we're so connected globally, and a lot of these connections from technology are really what drive the demand for air travel commercially from a physical standpoint. You look at some of the growth in the number of websites, the number of smartphones, how payments are being transmitted between workers back home to families in other parts of the world. Dramatic increases over the last 20 years. And you think about those conveniences, those enablers are actually helping people experience travel, demand travel, and actually get value and provide value in travel. And that's really what I see as the connection between aviation and technology in a global sense. So those long-term fundamentals, driven really by global economic growth, but also the emerging middle classes, the demand for connectivity, the need for connectivity, means that over the next 20 years, we expect passenger traffic to grow between 4.5% to 5% per year. I want to caveat that just very quickly because this is on a 2023 base. So globally, the passenger traffic around the world was still slightly below 2019 levels at the end of 2023. So the better way to think about it is if we go back to 2019, the average growth rate from 2019 all the way to 2043, so say a 45-year growth rate, or sorry, 25-year growth rate, would average about 3.5 to 3.7% per year. Long-term trend, historical that you saw on that curve is 5%. So we're pretty conservative or moderate as the industry continues to grow. As we do see some short-haul substitution, we still see tremendous healthy growth demand for the market. And so the fleet, on average, will grow just a little bit above 3% per year. The way that translates to airplane demand is that the industry is going to need about 44,000 new commercial aircraft above 50 seats. I'll caveat that again because I know the panel will talk about emerging technologies. These are, in our addressable market, jets above 50 seats for the next 20 years. And you can see the segmentation here. We think airplanes that generally serve single-aisle markets will be about 33,000. So the 80% of the market are largely single-aisle aircraft. And about 9,000 aircraft will be wide-body jets, either passenger aircraft or freighter aircraft. And just to put that in perspective, because again, what's 44,000 even mean? Divide that by 20 years, you're a little bit over 2,000 aircraft a year. The best year that the industry had in terms of producing these commercial jets was 2018, when we collectively delivered around 1,700, 1,650 commercial jets. So as an industry, we need to work off the backlog of pent-up demand, pent-up retirements, and get back to pre-pandemic levels and then back above that to satisfy the growth demand in the marketplace across all these different segments of the market. The other thing that's never been more diverse is the regional demand for commercial aviation. You can see here the balance, and roughly 20% per region between Eurasia, between Asia Pacific, North America, China by itself as separate from Asia Pacific, and then the rest of the world. And these emerging, developing, and mature markets help us, in terms of diversification, understand the dynamics that will come into play over the next 20 years. When we think about sustainability replacement, only about 6,000 aircraft that were in service last year will remain in the fleet in 2043. The rest of them will come from new deliveries. About half of the new deliveries will be used to replace existing aircraft, especially in mature markets like Europe, US, Northeast Asia. And the rest, about half of the deliveries, will be used to grow global fleets, especially in developing and emerging markets. So we see the global fleet growing from about 27,000 aircraft last year to about 50,000 jets in 2043. And just a reminder of the kind of those enablers that come into play. Aviation is fundamentally connected to the global economy, but aviation also outgrows the global economy on an annual basis. So as we look at history, as we look at the future, we continue to see a multiplier effect in terms of aviation growth or traffic growth outgrowing the global economy. So from a GDP growth standpoint, our future expectations between 2.5% and 3% will be coupled with passenger traffic growth rates above that level. So between 3.5% and 5% growth per year because of what aviation enables in terms of connectivity, in terms of visitation, in terms of just the utility as part of the global transportation system. A lot of that, I said earlier, is enabled by the affordability of air travel. And I think another way to sort of set up the future panel here is to think about where we've been. Over the last 60 years, since the beginning of the jet age, innovations in airplane technology from a commercial jet standpoint have reduced the noise footprint of jets by about 90%, and fuel efficiency is more than 70% better than it was when 707s, when DC-8s were flying around the commercial network. So again, there's a relationship, a correlation that continues, and it will continue on as we continue to put and place new technology aircraft into the market. From our perspective, our goals are both near-term and long-term. The airplanes that we're delivering today provide about 20% better fuel efficiency than the airplanes they replace. But then there's also what's next, right? How do we continue to develop and innovate for future platforms, for future aviation needs, and provide solutions for the market that is fundamentally a growth market, And it's not just about airplanes. Obviously, fleet renewal is what we're focused on today. Operational efficiency is something technology can help us with so that even the airspace that exists today can be used more effectively. And then really the big leap forward is how do we utilize renewable energy to really make a meaningful, scalable difference in terms of carbon emissions over the next 20 years. Advanced technology I'll leave for the guys behind me, but thinking about that, those are the things that were almost beyond our commercial market outlook. Initially, some of these disruptors in the marketplace really will be complementary to today's commercial aviation infrastructure. The smaller, maybe the urban mobility or the smaller platforms will help connect to the current commercial aviation infrastructure. And then long term, how does it scale to an airplane the size of a 737? How does it work in a future infrastructure, whether it be airspace, airport, or just from a power required element when we look at what is needed for long-range passenger travel. But again, just to sort of set the stage here, our market has proven itself to be resilient, probably through the biggest challenges that the industry has ever faced. Recessions are nothing when it's compared to the pandemic, and still then, the industry has proved that it's remarkably resilient, and it's because travel is so important. Connectivity is so important. This is a long-term growth market. Even if we're off by 1,000 or 2,000 aircraft, we're talking about a market that needs to be meaningfully larger than it was before the pandemic. And in order to enable that, in order to provide efficient growth to the market, we're going to see continued innovations from our side, from other players in the market, and build on that competition to develop solutions that provide growth for everybody. So hopefully that helps tee up the discussion, but you get a sense of how resilient our market is and how fascinating and dynamic commercial aviation will continue to be. So thank you very much.
Ladies and gentlemen, please welcome Aviation Guiding Coalition member Dimitri Mavris, Distinguished Regents Professor, Georgia Tech, to the stage.
Good morning, everyone. I hope you're having an exciting morning. So we're going to continue in this theme. The panel now is following from the excellent presentation that Darren gave us in terms of the future, the market forecasts and the like. So the stated goal of having air transportation becoming net zero by 2050 offers us enormous challenges and opportunities. Manufacturers and operators are already putting plans in place to revolutionize the way air travel is delivered, converting to new sustainable fuels, to transitioning the aircraft to electric propulsion, modernizing operations, and all of that is encapsulated in the Waypoint 2050 study that the industry has put forward, and also from ICAO in the long-term aspirational goals. So there will be challenges and obstacles. In fact, all these technologies that will be proposed here today are facing certification, regulatory type of obstacles, and also they will be facing some infrastructure comments. So we have assembled here a very good group of people that will give us different perspectives. We're going to start with Michael Drake, who is the Chief Airplane Architect and Senior Technical Fellow at Boeing. He's going to give us a broader perspective. We're going to follow with Dr. Volker Gollnick, who is the founder and head of Institute of Air Transportation at DLR and Technical University of Hamburg. Then we're going to follow up with Scott Savian, who is the Chief Product Officer at Jet Zero. And we're going to end with Ben Stabler, who is the Chief Technology Officer at Heart. So at the end of these presentations, we're going to have plenty of time for Q&A. So please keep these questions coming forward. So Michael, we're going to start with you.
Thank you, Dimitri. Let's see. Go ahead and get our slides going. Just leading off, I just want to say that we really are kind of facing a very exciting times going ahead. The topic today was kind of leading out towards towards 2050, and as I like to joke around, we have a lot of big challenges, and the answer is not in the back of the textbook. So possibilities aren't super clear on how we're going to address the different challenges we've got. And that's exciting for the people that are at this conference. We'll go ahead and go to the next slide, or actually, I will go to the next slide. And you just saw this chart from Darren. So the challenge that I'm going to focus a little bit more on our talk is a little bit more around the large commercial aircraft aviation. But I don't want to dismiss that the Boeing company, we're very engaged in other and emergent market technology developments. There's a picture of our Whisk aircraft. It's unmanned, vertical, electric-powered eVTOL or urban air mobility style or class 4 airplane. There's emerging markets around, again, the lower end that may be enabled by new technologies in addition to the commercial transport kind of bread and butter mainstream areas that Darren was just covering. Before I go too much in the details, I did want to say that an overarching theme and a principle is, and as I carry personal, is I believe, as Darren was saying, aviation and commercial aviation is a force for good and benefit for us all. But we've got big challenges. Sustainability and climate change is a major one. And so our tasks that we collectively have is what can we do to continue to allow commercial aviation to thrive and not be stunted as we address these big challenges that we must address. Darren talked a little bit about fleet renewal. I'm not going to say too much about that. We've got some super efficient airplanes that is generationally more efficient than the airplanes that are preceding them, that are in development, and will be depended upon as we replace the current fleets for improved efficiency overall. I'm not going to touch too much about that. More market-based measures. We're going to talk more about these central three operational efficiencies, renewable energies, and advanced technologies. It's good to know where you've been, where you're at, and before you discuss too much of where you're going. Coworker of mine was showing me this very chart and said, "Oh, I got to steal this." Darren just showed you a chart where commercial aviation's progressed about a 70% efficiency gain in fuel efficiency over roughly the last 70 years for jet transports. So about 1% per year. So I had another chart I was going to show, and I saw this one. This is great. Now, Cascade, for those of you who aren't familiar with it, is a modeling tool that's been under development with our Boeing team that takes a network look at the world. And you can basically model the impact on emissions for different assumptions for different markets, different aircraft categories. And so if you look at the categories here on the right-hand side, there's fleet renewal and future aircraft substitution or efficiencies in future aircraft. And so you can kind of play with the dials. You can kind of do the slider dial and say my future airplane is going to be 10% more efficient in this market or 20% more efficient in that market. You kind of look at a net effect on a global impact manner for a variety of parameters. So this is a fleet network averaged efficiency gain. So it's not quite looking at the same category of airplane coming on. And it, again, it reflects the same general message of the efficiency gains that we've been under in the first decades of commercial aviation. Where you're seeing about that 2020 time period right there, and it branches out, the purple, the blue, the red, those are just the effects of the Cascade tool adjusting, well, what ifs? What if I can get operational efficiency 10%, 12%, 14% better? How much impact would that have? And again, it's a very educational tool that's kind of used to kind of get a context for where the levers of impact as we look in our planning going forward towards towards 2050. This is another a context-setting chart. It's been used by some of my compatriots from Boeing before, and that is kind of like where's the fuel being burned? Where are the emissions occurring from? And it relates range with departures. Now, I have a love-hate relationship with this chart, and I'll explain why. And that, first of all, it's very useful to say, well, where are the emissions going on? If it's down at a 600 or 1,000 kilometer flight, those flights don't burn a lot of gas with the sheer range. And where the fuel is burned is with these larger ranges. And in fact, you kind of look up and go, well, at 87% of the departures, you're only at half the fuel burn for the industry. Now, the reason I have the hate part of this is not all departures are the same. People have been using this general intent or message. I like to normalize it, or we like to normalize it, Boeing, with seats. An ATR or an Embraer regional jet doing a 300-mile mission is not the same impact as a 777 or an A380 class airplane that's flying a 6,000 nautical mile mission. So you kind of have to keep in perspective that it's just a way of conveying, but where's the fuel being burned or where the emissions are happening? If you take a normalizing for size of aircraft, and as Darren was just saying, he measures where seats demands between city pairs. So set aside the airplane size, which is how many seats need to be served between different city pairs as we forecast around the world. And if you normalize the seats, it kind of stretches out the top on an equalizing basis. And I didn't have time to kind of pull that together, but my message simply here is we look at the different market and segments. I'm trying to figure out, well, what's the potential opportunities for the market segments, the decarbonization and the improvements in efficiency and sustainability there. One of those categories we mentioned on the cascade model was operational efficiencies. And in the operational efficiencies, we've got 60, 70 type of discrete technology ideas and proposals that could add up or would add up to roughly a 10% type of opportunity for operational efficiencies. And what are those categories of operational efficiencies? Some are just the more efficient ground operations, care and feeding and updating of your aircraft that you've got. Air traffic management is probably opportunities kind of roughly maybe in a 4, 5, 6% range of improvement for fuel efficiency going forward. Our ability to have just more direct routing, more idealized or matched, tailored routings for the conditions of the day has just been improving. We've got better technologies to improve that domestically, internationally, over ocean. I was just in a flight to London last week. It was going great, 787-10, Seattle, London. We get almost to landing, and the pilot comes on and goes, well, our timing's just off. We've got our slot arrival conflicts at Heathrow, and so we orbited for 20 minutes. Beautiful day, weather was good, and so that orbit for 20 minutes was just emissions going out the tailpipe. So the industry is working to come up with efficiencies and means and tailoring so those type of inefficiencies are washed out, the routings are more direct, and a lot of great work there. In our EcoD program at Boeing, we've just got constantly different of those, like I said, 70 type of ideas to work through. Almost every one of our EcoDs has got something along those lines as a technology proving ground. I'm going to talk a little about reducing kind of the classic. These are like the Breguet equation sort of classic type of items for aircraft efficiencies. The weight efficiencies, structural, aerodynamic, propulsion. I just simply don't have enough time to elaborate on the details or getting into specifics around the particulars here. Propulsion technology has been a big, huge driver, and how we wrap an airplane and integrate and complement the propulsion technologies of the aircraft is ongoing. We're certainly working very tight with our engine manufacturers, looking at potential new engine concepts to work out the merits. I'm also going to talk a little bit about the emergent or the emissions via the fuel approaches. I'm going to get on this right here. So you saw the picture of the X66. So that's an example of what we think is a very promising technology around the vehicle design aspect and efficiency of the aircraft. We actually think it's the most promising and efficient approach, particularly around the single aisle kind of size category. The airplane is well underway. It is a span machine. I've been designing airplanes for 40 years. And as you look at every airplane I've worked on and developed, there's always a balance between, for example, in a wing design and aspect ratio and sweep. You increase the aspect ratio to the point where the benefits of increasing aspect ratio are offset by the penalties, where the induced drag reductions are offset by the weight increases, which is also a form of induced drag. And so is there the step function change where we can enable a more efficient span, weight, efficiency trade space with this architectural approach than with the classic. Now, one of the things about an X-plane airplane is it's not intended to say we can prove a certain L over D. We can do L over D and wind tunnel testing and CFD. That's not the point. The purpose of the X-plane is to figure out and work out the architectural nuances and developments in particulars, the aeroelastics, how the airframe and the aero works. It's also, trusses have been on airplanes. I own a 1946 Piper J3 Cub. I've got a truss on my airplane. It's Mach 0.1. I have a 90 horse airplane, 85 miles an hour. So not Mach 0.8. So how to get these merits and integration at the cruise speeds that are reflective of how the network and efficiencies are today is where we're after. Now, again, the airplane's well underway. This is a picture out of our Langley test with our NASA compatriots. I'm pretty sure I've got to see if you get, oh, there's one over here, that we're working on, and I'll be down at Ames in a week or two where we've got further testing going on down there. So this is for, I think this was a deep stall, high angle of attack type of test facility, or results we're just getting out of this test. So we've got the momentum going, the team's going full charge ahead, and we're getting great lessons. We don't have to wait till the last flight test to know what we need to learn. We are learning along the way, and the learnings in the X666 is informing our team in our product development in terms of not figuring out how to make a truss brace wing work, but how to optimize and exploit the potential of the truss brace wing. And that's the purpose of the demonstrator. Briefly on SAF and sustainable fuels. So SAF is our future. Our goal, a lot of our problems, I took a first order physics challenge, is we've got 420 parts per million CO2 in the atmosphere, and it's going up. SAF uses carbon that's already in the biosphere. SAF is using biostocks, SAF is using source materials. There's many different flavors of ice cream with SAF, as I like to say. The HEFAs, Fischer Tropsch derived from different feedstocks, and they enable a reduction in net CO2 by using the carbon that's already out. It's not pulling it out of the ground. That is, and it's compatible. And we're currently at a 50% blend. We're designing airplanes so the end of the decade will be 100% blend, 100% SAF capable in our aircraft, and that works ongoing. There's non-CO2. I'm running a little short on time, but the non-CO2 part, contrails, we don't want to ignore NOx, contrails, and other emissions impacts. I had a great flight test with a DC-8 from NASA. It was chasing behind our 737-10, flying different blends of and mixes of Jet A and SAF, and we were getting great data on the different and favorable, actually, contrail characteristics that come from burning SAF than straight Jet A. So SAF and I want to talk a little bit about process. So we don't know what the answer is yet for what's the and. We think there's an and. SAF is part of our future, absolutely. Is there an and? Now this chart doesn't say what the and is. It's basically intended to talk about process. So if we look at where's the source energy is coming from. Wind solar for green, is it coming out of the ground for Jet A? Fossilized stored energy has been aggregating over the millennium. And then how is the energy, source energy, how is it carried? Is it carried in the Jet A, that long chain molecule? And you can kind of go down, there's SAF, hydrogen's on the table, but hydrogen's also, there's other hydrocarbons, ammonia, I get asked about ammonia all the time. So we're assessing the different options and the pros and the cons and the merits of the different fuel systems to sort out what's the best proposition. And down at the bottom, there's energy carrier is batteries. And so, and as you go across, is how is that energy converted to useful, productive thrust and into the vehicle. The real thing I wanted to talk about process-wise are the notes over on the lower right-hand side, which is, do the physics work? Do the physics make sense? Can we use this combination in a safe and certifiable manner? Is there a value proposition? And then what's the impact to the relevant stakeholders? And as we spiral through these considerations, we look at kind of how the TRL, I actually kind of think of it as spiraling up, how the TRL gets advanced. And the TRL stage is, kind of the early TRL 1 to 3 is kind of this discovery phase, kind of something of interest. TRL 4 is more of, is it feasible? And then you're not really getting into the practicality stage of the TRL 6 to 7. Now, how many people in the audience have heard about the TRL Valley of Death at TRL 6? Right? I see a lot of hands, so you know what I'm talking about. The thing is, for something to be feasible, a lot of hard work to get to that stage. For something to be practical is the point where you only need one impractical thing to sink everything else. So are all the balance of the ilities, the manufacturability, certifiability, maintainability, durability, in balance and in totality going to make sense? And then the last thing on the TRL doesn't get a lot of news, and that's the applicability. So if a battery technology comes up that's twice as good as the current battery technology, well, on a 787, I've got a more electric systems architecture. That's great. I'll save some weight, maybe fly another passenger on that airplane. But if I'm talking to Brian Utko and our WISC friends, and he gets a battery technology that's twice as good, well, that's propulsive technology efficiency. That is a far greater impact. That same technology could be a really big enabler for a WISC category electric vertical urban air mobility. So it might make sense, but with a different impact and for where those technologies develop and mature. So I don't want to spend too much time here on the advanced technologies, simply all electric architectures. We've got those, we're looking at those. You're not going to see an all-electric 777 class airplane flying 5,000 miles. The technology is just too far of a leap. It's just not practical. It's not even feasible, much less practical. We're looking at hybrid electrics on propulsions. We've got some teaming. Supporting our Aurora Flight Sciences team is working with GE and NASA on a contract, the EPFD, Electrified Propulsion Demonstrator. It's putting a hybrid electric architecture on a Saab 340. And so we're trying to figure out what's the potential of that technology. Is it feasible? And then once we get the feasibility, we'll start thinking about the practicality and the applicability of where that technology might apply in the aviation, commercial aviation space. Cryogenic fuels, hydrogen fuel cells. We're looking at hydrogen fuel cells and opportunities there. Again, you're not going to see any 787 category hydrogen fuel cell airplane. The technology is just not even feasible. But where might those type of technologies be applicable all the way from, again, the WISC category up through? Enabling technologies, I will simply say the automation and autonomy deserves a whole nother talk. We got a lot of, the least bored people that I run into, least bored engineers I run into are our team that's putting autonomy systems on our Caravan and taxiing around and having it being chased by cars and stopping, dodging, and avoiding, in-flight, auto-land. There's a great deal of work there. The one thing I just want to say with autonomy is we're looking to enhance safety with autonomous systems. We will not be kicking pilots off airplanes anytime soon. We're trying to complement and enhance what the vehicle-pilot combination can do going forward. It's really more of our philosophy there. And I think I'm out of time, and I'm just simply going to leave. We've got a broad portfolio of activities that we're under development for small to large, near term, medium terms, and far terms. Again, a little bit about the process. Again, we don't know what the answer is in the back of the textbook here in terms of what that world will look like in 2050, but you don't know unless you try and do and fail and stumble and learn and along the process along the way. And with that, I'm out of time, and I'm going to hand back over.
Thank you, Michael. Volker?
Yeah, good morning, everybody out there in the dark. And I like to put another perspective to the modernization of the commercial air transportation system. And we all know, and I think we all should be very happy to see these big success stories we have seen during the last decades. We had the wonderful aesthetical Dreamliner aircraft. We have seen the high technology A380, which has a similar weight like some 10 locomotives we see on the railway. It's a tremendous and immense engineering performance we are facing there. We have the high production rate aircraft like the A320, but also on the long range, the 777. So why shouldn't we be happy, relax, and sit back? Because there are some duties. And we all enjoy the value of time we spend in a comfortable cabin, but we also enjoy the time we save if the aircraft are flying a little bit more fast. A couple of days before, I read in a German magazine, the CEO of EasyJet requests for more flights. Is this really necessary? I think the key question for modernizing the commercial air transportation system is how can we ensure individual sustainable mobility in the future where we also can mitigate the climate impact? And that's, for me, the key question we have to answer. For that, I think we have to set up a balance for the future, and it's not only a technical one or ecological one. On the one hand, for sure, we have to ensure sustainability by long and efficient use of resources like materials, but also efficient use of energy. Second, and that's a different topic, minimum impact of emissions in all phases of the air transportation system life cycle and in all stakeholder or subsystem areas. That's the one major task we are facing. And on the other hand, I think we all, as privileged engineers, we have the responsibility for this rest of society, and that's an economical one. We have to ensure economical growth, at least welfare, by ensuring employment. We have to provide some kind of profit, but also we have to establish and create economical relevance of the entire aviation industry. And there is one subtopic we should address in that field, which is about the identity of aircraft and cabin. I think we can understand an aircraft as a capital good, which typically has a long lifetime. But cabin and all the services around flying are more understood as consumables. How can we take these characteristics to modernize the entire air transportation system? Now, I think we all agree there are various areas of modernization we can take. And this is first, think about new air transport system architectures. Also, operations provide a wide area of improvements. Also, the air transportation system infrastructures, airspace and airport, have some areas where we can definitely improve. And at last, Mike has addressed this intensively, also aircraft technologies provide some areas of improvement. So, air transport system architectures, something new. Advanced air mobility, we are talking about that in various sessions throughout these days, provide a new way of individual mobility. We can save time, we can improve travel comfort through reducing stress and traffic jam. And on the other hand, some are also thinking of flying very fast, and this is also an option for a new market business. And I think both new architectures have one thing in common: they raise emotions. And that's something I'm missing from time to time when we are discussing about hard technical stuff. Where are the emotions of creating something new? And these areas, advanced air mobility and also supersonic flight, raise emotions. But they can also provide new markets, but may be limited in sustainability and climate impact mitigation. The area of operations provide various aspects of improvements. Like, for example, climate impact mitigation trajectories. You've seen at the top left, top right sketch, 3 different trajectories. The one in the middle is a great circle trajectory. The one above is the trajectory which creates minimum cash operating cost. The lower one, on the other hand, creates minimum average temperature raise. So you see, by adapting operational procedures only a little bit, you can improve a lot, but for sure there is a price. Flying slower and lower is also a procedure which has been proven as something which can really reduce the climate impact of aviation. Or another procedure is evade climate effective atmospheric areas. Low emission ground operations offer the potential to improve the climate or the local air quality and also reduce the local noise. This implicitly has also a big positive impact on the entire climate, not only on ground, but also in the entire atmosphere. And there is another topic where maybe aircraft manufacturers may be a little bit concerned about, but frequency reduction versus larger aircraft can save roughly up to 6% fuel with the associated emissions. And this procedure can also reduce the airspace capacity congestion. On the other hand, if we use larger aircraft, we have the opportunity to provide individual air mobility as it is requested by the societies. So these are actual operational measures we can use to mitigate the climate impact of aviation right now, today, with the existing world fleet. There is another perspective which is about new propulsion systems. Mike has addressed some of those. Why shouldn't we go for adapting operations to the available capabilities of technologies? What does it mean? For example, electric flying is not able to allow for flying 16,000 kilometers, but we can, on a midterm perspective, achieve 1,500 kilometers. If we create and build aircraft which, with electrical drives which fly 1,500 kilometers, we have to change the air transportation system architectures. So this is another operational measure we can use to improve and modernize the air transportation system. Looking at the air transport infrastructure, terminal processes, we all realize this, are sometimes a nightmare. We have to pass the security gates, we have to do the check-in, and improved processes here in the terminal, maybe using AI algorithms to let the people's flow more fluent, can improve the quality of service. Air-ground operations like fully hydrogen or electric vehicles can improve immediately the air quality and the noise impact. And hydrogen, for example, is something which is mainly associated with some kind of mass for storing it, and it has an impact also on the specific energy density. But on ground, this is not a big issue. So we can use hydrogen on the ground and can make use of the advantages. Airport aircraft handling capacities are close to limits. When we arrived last week at the airport, we were waiting nearly 1 hour close to the gate because one aircraft was still standing there. Why shouldn't we develop processes, algorithms, and procedures which can improve this and make the handling of gates more flexible? This will improve immediately the quality of service at the infrastructures. And at last, the airspace capacity. Is it really wise to squeeze more and more aircraft into the airspace? At least at home in Europe, we have a big capacity issue. And I'm not sure whether we should put more and more aircraft into the airspace just to ensure air mobility. Why shouldn't we put more people into the aircraft? Another area is about aircraft technologies. And I refer again to Mike Drake that he has introduced some propulsion technologies which for sure can immediately reduce the climate impact. Mass-saving measures, more sandwich structures, for example, can reduce the energy effort of an air vehicle. Fully recyclable cabin provides sustainable but up-to-date services. And remember, a cabin can be understood as a consumable with a reduced lifetime. In this area, it makes definitely sense to look for fully recyclable cabin architectures, cabin materials, which can really use the materials more efficiently, more sustainable than we do it right now. Another technology in the field of aircraft technology is the single pilot cockpit. I think here the answer is quite simple. The single pilot cockpit can contribute to cost reduction. I think that's a simple thing. So, in summary, aircraft technologies provide benefit for profit, for cost reduction, but also for climate impact reduction, but more on the midterm perspective, because we cannot change the entire world fleet within a couple of days or weeks. And that's a major difference between technology impact on aircraft and technology impact on operations and infrastructures. If you look on a more high level at the evolution of aviation, you can compare it a little bit with the so-called Kondratiev cycles. And for sure, there is a question, what's next? For me, as an intermediate resume, because aviation is never at the end, if we really commit to sustainability and climate impact mitigation, this requires a different modernization path. I think less but larger aircraft or aircraft with higher capacities can allow for more efficient use of energy and emissions generation, and also allow for more efficient use of materials. But the lifetime of such aircraft may be longer. Less but larger aircraft support capacity limits avoidance in air traffic management. The consequence of such a change in the development of aviation is that we have to transform the industry more from production orientation to service orientation, because this is really the support of sustainable use of resources and provides new employment, but in different areas, including maintenance, repair, overhaul business, which is for sure an increasing business. Operational measures enable climate impact mitigation now, and that's an important point. Aircraft technologies are more oriented to midterm perspectives. And at last, new air vehicle concepts raise emotions and may offer also new business. And I think that's very important when we look at the next generation of young engineers. Emotions is something which drives us to move forward. And that's what I wish for the aviation industry. Thank you.
Good morning. My name is Scott Savian. I'm with Jet Zero and happy to represent our whole team here today, and super excited to talk to you about the blended wing body aircraft that Jet Zero is in development on, with a mission to reshape aviation. And to understand what we mean by reshape aviation, it's actually kind of nice to take a walk back. It's actually remarkable that from 1903, Kitty Hawk, all the way to 1963 and the dawn of the jet age is the same amount of time as from 1963 to today. Should I hold a sec? And those first 60 years were remarkable. The amount of innovation around the airframe was almost stunning and no holds barred. We saw some of the craziest ideas and everything thrown out there. And the industry eventually settled on a tube and wing design. And that design has served us exceedingly well. It ushered in the jet age. It literally has helped create the world as we know it today. But like most technologies, that airframe has started to max out. The fuel efficiency gains that we see are mostly driven by engines today. And in fact, the cabin itself, where our colleagues here have noted that we've not only densified the cabins, but we've pretty much hit the tipping point or the peak of our ability to fill them. And so an aircraft designed decades ago to, let's say, hold 145 people that's routinely holding 180 plus, is challenged. The space is challenged. And we feel it. Not only the passengers, but the crew. And yet, despite that continued pursuit of driving costs down, the margins in the industry remain compressed. It's a hard job to be an airline. 2 to 3% profit as an industry is a good year. And even a run of a number of good years in a row can run into a single event that wipes out a decade of profits. But remarkably, COVID is a fraction of the cost to achieve net zero by 2050. magnitudes more in investment required to get us there. Much of it in SAF, which we believe heartily in, electric and hydrogen as well. And that goes before we have to understand that the cost of that sustainable aviation fuel is actually going to go up into an industry that drives its growth through keeping costs down, and it doesn't have the margins to absorb that. So we believe there's a better answer. It's an investment in a new airframe, the blended wing body, that ushers in a step change in efficiency, up to 50% lower fuel burn and emissions out of the gate. And all of that efficiency is driven by the airframe itself. This is on today's engines. A single aisle engine lifting 250 people for longer ranges. Well, like many projects, when you get into the blended wing body, you actually start, and you get into this new shape, and you get out of the past, you start to discover a wealth of opportunities that go beyond just efficiency. We take for granted things like efficiency usually means less comfort. Sustainability often increases costs. But what if an airframe could actually buck that trend and have efficiency without compromise, a shape to transform our experience? This is our hangar in Long Beach, California, and we're working on how to deliver your best flight every time. In a 250-passenger nominal aircraft that boards in under 12 minutes, has a dedicated space for every single person's bag. You never sit more than 12 rows from the entrance, and has unique spaces inside. We're addressing accessibility issues right up front, and every seat on the plane is larger than the class it replaces today. And the shape offers more than that. In a head-to-head comparison against aircraft, it's highly beneficial. But that shape actually opens up a wealth of opportunities going forward as well, and can help accelerate the path to zero. It starts with the ability, we can't take a tube and wing aircraft right to that unicorn mid-market size. Our shape isn't beholden to the square cube law, and we can size ourselves to go right in the middle of the market to capitalize on two of the trends that were mentioned earlier, the upgauging of the smaller aircraft, but also giving the range capability so that the trend in smaller wide bodies is actually supported. And it's that range capability to do it with comfort and efficiency beyond today that allows us to, with a single airframe, a single aircraft, address up to over 90% of the market if we measured it by revenue passenger miles. We stand on the shoulders of Mark Page and his colleagues who developed the idea back in the 90s, and we benefit from over $1 billion in NASA research that's gone into blended wing body, aerodynamics, flight control, and structures. And we're putting together a coalition of the determined. Some of the best in the industry are coming together with a vision to help this aircraft succeed. With investors and supporting the long term. NASA was our first supporter, and the Air Force is our biggest to date. We have 2027 full-scale flight demonstrator that'll be happening. And that's our primary focus right now. And we're putting together a team to reshape aviation, a team that wanted to come together for the purpose of the mission. Mark Page, our founder, and Tom O'Leary in the top corner there. Mark gave a presentation at an event like this where he talked about blended wing body. Tom and Mark had met at Beta. And Tom came from early days at Tesla. And after Mark's presentation, Tom said, this plane has to happen. Every single person on this page had the exact same reaction as they got to know the plane. And that's how our team's been built from the bottom up. It includes notable folks like Rob Dewar, if some of you might remember him, and I could go on. And so the remarkable thing about the plane is that mid-market position, the ability to run multi-missions more efficiently, more comfortably than today, a transcon operation that's a logical replacement to a 767 or a 757, but also run short-haul operations more efficiently where upgauging actually helps reduce congestion, and still have the legs and cabin capability to do 4-class international service. A single aircraft that can run multiple missions across the breadth of the world's operations. That's enjoyed by airlines. If you're a low-cost carrier and like a single aircraft model, you can actually open up new city pairs and markets. If you're a mainline carrier and you have 10 or 12 different aircraft in your fleet, you can simplify your fleet. And so the benefits are compounding here. And its ability to address this large chunk of the market means we're literally talking about a climate warrior, a mid-market workhorse that can move the needle on climate. And it does it by immediately reducing emissions on Jet A by up to half, flying further and more effectively on SAF. It'll benefit from any new engine technologies that come along. And critically, because it uses less energy, it makes things like hydrogen and electric propulsion actually more viable. And it's doing all this at scale in an aircraft that actually moves the needle on sustainability. So this is our mission. And it all starts with the shape. Thank you.
All right. Hello, everyone. My name is Ben Stabler. I'm the CTO at Hart Aerospace. I do have some slides. Oh, here we go. All right. So I'm the CTO at Hart Aerospace. We're going to be talking about a smaller plane now. So we're a Swedish company. We're building a LA office for engineering. And our mission is to democratize and decarbonize air travel. And so, what do I mean by democratize? So we've talked about the sort of changing landscape of air travel. Today more people fly than ever did before. The cost of flying sort of normalized for real world money is lower than it has been before. But we're also seeing a reduction of service to regional airports, and this has been going for decades. And obviously there's significant challenges on the environmental side as well, which are starting to become more of a talking point, particularly in Europe. And one of the reasons why we've seen sort of this pullback on regional transportation is because the economics of the jet engine make it difficult to serve short distance routes and smaller airports. And so one of the challenges is that the fuel burn on a per kilometer basis is much higher if you're going short distances, and obviously that translates into higher unit economics. And another challenge is that the maintenance, which drives a significant portion of the unit economics as well, is much more challenging on smaller aircraft with a turbine than it is on a larger aircraft with a turbine. And this is another slide, and this is a slightly different interpretation than some of my colleagues have shared. But if you look at the CO2 intensity, about 30% of the CO2 produced, and also the passenger kilometers are on short distance routes, so routes that are less than about 1,000 miles. So there's a huge opportunity in the short distance market, in the regional market, which these renewable technologies can address. It's also a cost factor, and then we talked about connectivity a little bit as well. There's a number of communities that were previously connected by air travel, which are no longer connected, that obviously creates a disparity between the access to transportation that these people have. So the aircraft that I want to talk about, this is the aircraft that we're building. It's the ES-30. It's a 30-seater hybrid electric aircraft, and it's comparable to a turboprop aircraft that you may have flown on in the Caribbean or in Europe. And so this is a hybrid electric aircraft. So we have two pure electric motors inboard on the wings. And then we have two conventional turboprop engines outboard on the wings. And these two systems are fully independent. So we can operate this aircraft in a pure electric mode, and that's how it will be operated for shorter distance routes. And then if you need to fly a longer distance route, or you need to handle a go-around or a diversion, then you have the ability to switch over to the turboprops. And we believe this is a pathway to a fully electric aircraft for these regional routes. And we also believe that it provides a accelerated path to certification for this aircraft. And I've got a few specifications for this aircraft. So it's a 30-seater. It's a relatively small aircraft. We are promising a 200-kilometer all-electric range at introduction to service. And so, this is quite a short distance on electric. But if you look at the average route for a turboprop aircraft of this sort of category, this covers most of the routes that are flown today for that type of aircraft, so it would be a drop-in replacement for operators there. And then over time, we're going to be able to extend this range as we improve the battery technology. We're targeting a 30-minute charge time, so this will, like I said, be a drop-in replacement for operators of small regional aircraft like this. And our goal is to certify this in 2028. So this is a chart that so JSX is one of our customers or future customers. This is a chart that they published at the same time as sort of announcing their partnership with us. And it really highlights the number of routes that are enabled by a hybrid electric aircraft of this kind, which can provide lower unit economics for these short distance routes. And so they project a 4x increase in the number of airports that are served by scheduled airline travel. And the impact of that is obviously that these are communities which are potentially disconnected right now, which have access to travel to a hub and then onwards on a larger aircraft. Now, if you look internationally, as has been discussed by my colleagues, we're projecting significant growth in the Asian market, bringing online many people who don't fly today. And so we think there's substantial demand, not just for the wide bodies out there, but also for this kind of aircraft, and especially if you take the decarbonization element into play here. So just a quick slide to talk about our market traction. So number of orders from regional operators, but also from some of the legacies who see it as an opportunity to connect their hubs to more communities. Obviously, our primary goal here right now is to deliver aircraft. so this is the future, but I just wanted to close out with a quick slide here that shows the test article that we're currently building in Sweden. So this is a full-scale demonstrator of our aircraft. I actually just got news from the team this morning that the wing has been attached to the aircraft, so it looks a little bit more like a plane today than it did in these photos. But we will be looking to start development testing with this aircraft in around the middle of next year. And that's what I've got.
Very good.
Thank you.
All right, so we came to the end of the prepared remarks. Obviously, we saw a very strong forecast in the demand, and we heard 4 different perspectives. So then the fun part begins when some of your more popular questions get to be addressed. So we have quite a few questions here. I won't be able to cover all of them in 30 minutes, but I'll do my best to get the ones that rise to the top. Don't forget to vote for the ones that you feel that should be addressed first. So the very first one is about what do you believe is the biggest issue plaguing new clean seat designs?
Happy to jump in there.
Okay. Yeah. Please.
Yeah, I think the challenge is, there's many pieces to it. Jet Zero came about because the ability to simply focus on one project was paramount for us and not worry about existing backlog and operations and so on. But there's a downside to that. We don't have backlog, we don't have revenue, so we need a lot of money to start the project. And we have great momentum happening right now as we move into our Series B. But the ability to push it to the finish line is probably the biggest question. I think there's a watershed moment coming up. The Air Force project to deliver a full-scale demonstrator in 2027 is our main focus right now. And when that aircraft flies at that scale, holding the cabin that I described before, then the industry literally will stand up and take notice in a way I think that'll be disruptive.
Mm-hmm. Very good. Yes?
I think another aspect could be also in the field of education. We typically educate our students to design a classical tube and wing configuration with all the aerodynamic structures and so on and so on. And we teach our students to calculate instead of designing it, something new. And what I'm personally missing sometimes is really the creativeness to design something following just the flow of shape. And I think this opens the mindset of students, of people, to think about something fairly new and to think out of the box. So I think also at the universities we should change a little bit the way of education, step away a little bit from hard coding, hard calculating, structured analysis, more to design.
Thank you. Michael?
I would echo that technology drives our business. It gives me the excuse to be able to do new airplanes as new advanced technologies. The extent at which technologies interact and integrate is daunting, because we don't just do one technology at a time. As much as I think the old Lockheed Skunk Works thing was like one technology at a time, I think was the quote. The spacing between airplanes now are such that multitudes of technologies have to be integrated to converge and keep up with the market. So that complexity, again, now you're doing something that's just not in the back of the textbook for conventional design. That creativity in terms of finding an integrated best solution. And then working the team sport aspect of how to get the many different considerations to optimize out is a big challenge, and it is pacing timing. It takes time, not just investment, but time to advance to market. And that's a balance that we're struggling with, is the investment, the time, the resources for developing and integrating the new technologies, whether it's shape, propulsion, engine technologies, open rotors, alternative fuels. It's particularly difficult when you have a new technology that doesn't have a precedent. And by precedent, I mean a prior practice that you could scaffold off of.
As you're heavily regulated, you're competing against yourself, there's a lot of risk, certification, right, all the stuff.
We live in a world of, something in education that doesn't get it, you can't possibly not have the time to get to all the considerations we get to. I talked a little bit about the ILITs, but you're exactly right. The certification, I live in a world where we don't get to sleep comfortably until our analysis says that the probability of a 1309 FAR failure FHA analysis is 10 to the minus ninth. And so, as I was saying a little bit earlier, there can be many things that are promising about a new technology, but if you find just that one, that's the showstopper or the brick wall, and you have to spend the time to work around, and again, that takes time and resources. So it's commercial certified aircraft. It's just so multi-layered and the considerations.
Thank you.
I want to put a little bit more of a positive spin on it than my colleagues. I think there's a mindset in the industry that it's incredibly expensive and incredibly time-consuming to design a new aircraft, and historically that is true. And so that kind of gets stood up as a reason to not pursue certain advances that we could otherwise pursue, and all of that is true. But if you look at other industries that have been affected by decarbonization or by some of the advances in technology that we've seen over the past couple decades, the hardest product to bring to market is the first one, and if someone is able to do that, many other people sort of realize that it can be done and sort of enter with and that's when you see these huge sort of steps forward in terms of the technology that is being applied in a certain industry. I think in aviation, certification is incredibly challenging, but the advances that have been made on software and hardware test over the past 20 years mean that if you do a clean sheet design today, there are opportunities to go a lot faster than we've gone in the past. And structures, airframe design, the advances in composites and automated manufacturing techniques, I think are starting to be felt by the industry and have been felt in other industries. And then on propulsion, some of these, incredible amount of work has gone into jet fuel-based turbines historically, and those are incredibly sophisticated machines. But some of these advanced technologies, like electrification, it's fundamentally a simpler and cheaper technology to construct an electric machine than it is a turbine, and we'll see advantages from that as well. So I think that it is challenging to build an aircraft. It's a very complex machine that has a certification bar that's much higher than most other industries, but there's also opportunities that haven't been fully exploited yet, and I think that's really exciting for the next 10 years as we see.
Thank you. The next question that popped to the top amongst the audience is, why don't we have a BWB aircraft flying today? What has changed that means that they're now the right solution?
Great question. We're kind of at a confluence of a whole bunch of new things coming together, and Ben quite aptly pointed them out, right? New technologies, the CFD models we can run today are highly accurate. Manufacturing, in fact, I have colleagues who will be Mark Page and Tim Berry will be joining our conversation later at 3:30 to get into those details. But we're at a place where we can actually make these things happen, and it's software. It's the ability to work together. It's things like Omniverse and new technologies around how we work to be able to develop a new airframe quicker, faster, and more efficiently. And part of it for us is a little bit about the strategy too, right? A blended wing body could be an overwhelming undertaking, but we have a high degree of off-the-shelf components, from the engines through avionics and as we work our way down. And so the challenge we're taking is fundamentally to deliver a new shape. And like I said, Ben's pointed out, the technology exists now. The technology exists in composites and manufacturing to be able to do that. So we're in a different position today.
Very good. Anyone else? Yes.
I think that since BWB is a quite new and different configuration, it's also a big production issue, and also a question of assembling such a new vehicle. If we have a classical tube and wing aircraft, we have well-established production chains, and this works independent of if you use commercial off-the-shelf components or develop something new. But if you have the entire design of the BWB, you have to segregate it in different components which are really manufacturable and also assemblable. And I think this is a quite different approach, which is challenging and which also costs a lot of area and place to do it.
Okay. Thank you, Volker.
I guess I'm being looked at.
It's up to you.
As been trying to sort out, as I bring newer configuration designers on board, you match the configuration to the requirements and the technology set, and it's always a horse race of what's the best horse for a specific set of technologies and market demands and sizing. So there's merit and attractiveness to attributes around the BWB. There's also impediments that have to be dealt with. Manufacturing and considerations, a full set of requirements commercial aircraft have to meet. The concept isn't family very friendly. There are concepts to make it family, but the commercial market needs different sizes of airplanes to different categories. And so although flying an airplane, it's either just not able to fill the seats, or flying an airplane that can't fill the seats because it's not right sized to the market. It's an issue or an item in terms of applicability of the airplane to different market segments. It's a significant factor for its appeal. Again, back to the certain markets, but I'll leave it at that.
Yeah, well, of course, people have looked at blended wing designs before, and I think that there's never been as much of a focus on fuel efficiency and decarbonization as there has today, and it's also never been as difficult to see the next percentage point in efficiency improvement with conventional technology as it has today. So I think that those are both factors that are pushing us to look at new ways to design aircraft. And I am extremely excited about what JetZero is doing. I'm very much looking forward to seeing their plane in the air. So I'm very excited about it.
Okay, thank you very much. The next question. Improvements in technology have traditionally been used to increase aircraft payload range capability. Do you think aircraft will now maintain or even slightly reduce capability but optimize for sustainability?
I guess I'll lead off on that. As Darren was saying, we're designing to match market needs. There is a feedback loop on the efficiency of the airplane in terms of how it affects the demand and the network pull. So the demand, as Mr. Hulst was saying, has been growing. Average airplanes have been growing in size. Doesn't mean there will not be demand for basically just about every market segment payload range that's out there. 787, when we were developing the 787, it wasn't just about I can fly the city pair and save 20-30% fuel. It did lower the economics for long-range flights and enabled more long, thin route city pairs. There's a tremendous number of new city pairs that were triggered by the efficiency of the airplane. So in terms of sustainability, if it's an efficiency play and the net economics to fly longer range on a more right-sized airplane, the market's going to demand that, and if we can provide it, that's going to flesh out. So it's not per se that a sustainable airplane, we'll be approaching sustainability at every market segment size that we're going to be addressing. The degree of impact will be a market-driven dynamic, not
Thank you, Michael.
based.
Yes, I think it's really an economical issue, mainly because manufacturers as well as operators want to have an aircraft which is highly flexible in use. And that's what we see if we analyze the real operations. So long-range aircraft also and short-range aircraft are operated mainly far below the design range. If you look at the global fleet. This means, in fact, that the airliners want to have an aircraft which they can use on short ranges, but also on longer ranges. And so payload and range is a driving factor. If we want to create the same fleet in a more sustainable way, we have to differentiate it and target to different ranges and to different payloads. And this will create a wide range of products and product variants, which is expensive and not manageable.
Thank you, Volker.
I don't know if we quite got the question down here, but I think I got the gist of it. I mean, this is one of the remarkable things about the blended wing body. As I mentioned in the presentation, the ability to go to the mid-market position because of a different shape puts us in a place where we can have impact both above and below our weight. And that ability to do that is actually unique. Not that big planes can't fly short routes today. They can't do it effectively. And this is an aircraft that actually can, with disruptive levels of efficiency gain, but actually a cabin commensurate with what the expectations of the future will be as well. And so it's a unique position that simply exists because of the shape.
Thank you.
Yeah, and to speak about the hard aircraft, we're targeting the very low end of the market, which is currently served to some degree by turboprops. Access to communities which can't be served or can't be served economically by narrow bodies or larger aircraft. And often these communities are most impacted by fuel cost and global warming as well. So we think that this is a really good entry point for an electric regional aircraft. And certainly we hope to see the technology be successful there and then also expand upwards as batteries get better in the future.
Yeah, thank you very much. Our next question is about hydrogen aircraft. Due to the complexity of storing hydrogen, has this approach largely been abandoned as a commercially viable fuel? Question, is that true?
Well, hydrogen is very challenging as a molecule, and this has been known for some time, both in terms of handling, safety, and the volumetric density. And the flip side, obviously, is that it can be if it's produced using a green technique, green hydrogen, it's fully renewable and without carbon content. So very challenging, but also strong benefits. I think for the really low distance stuff, like what Hart is working on, if you can get away with just batteries, then avoiding the efficiency hit of having to produce your hydrogen is a pretty big advantage. You can be a lot more cost effective with a pure battery solution than a hydrogen solution. And I think we're seeing that not just in aviation, but across most industries. If it's possible to do it with pure batteries, that's generally preferred and generally yields a lower cost solution. And if it's not, because your energy demands are higher, that's when hydrogen starts to be interesting. So I think there's still obviously sad news that Universal Hydrogen closed their doors recently, and they're also based in LA, so we know them. So there's a lot of challenges there, and I think it's not dead, and there's a lot of work going into it still, but big challenges to face as well.
I think from our side, so we're big fans of hydrogen, as we are SAF, and the challenge with hydrogen, right? It's energy per pound is in our favor, but the volume is huge, right? And so one of the things a blended wing body enables us to do is to centrally locate the hydrogen around the center of gravity. So as we deplete it over time, we're depleting it with the aircraft in balance. But because we're using half as much energy, we need half as much volume to run the same type of missions, or we can run up to twice as far on the same amount of volume. So there's a reason that Airbus is signaling potentially a blended wing body hydrogen aircraft, right? It's because it's an airframe that dovetails very nicely with the technology. So we're actively planning to be ready for it when it comes. We're not developing the technology ourselves, but we're big fans. And our airframe that holds 250 passengers nominally on Jet A or SAF will actually hold 180 to 200 passengers and be able to do transcontinental routes on hydrogen, and even a little beyond, meaning if you had a hub with hydrogen, you could potentially run multiple flights and end up back at your hub to refuel at the end of the day.
Very good.
I think the storage issue is the most important one in an aircraft. For sure, blended wing body is well suited to store hydrogen in the vehicle, no problem at all. But on the other hand, you can store hydrogen either with cooling or with high pressure or both. Both technologies are associated with high mass, and that's something we don't like in an aircraft. And so that's really a crucial point. And the other thing is, I'm personally a little bit concerned. As far as I know, if you have hydrogen of about 4% in the air, it's able to explode, and I won't feel comfortable having this kind of fuel in the aircraft when I'm across the Atlantic. So that's a real challenge, as you have mentioned. My personal favorite is indeed to use hydrogen as much as we can on the ground for various purposes. Their mass doesn't play a significant role. Also, safety is not that crucial as in the air. And I think that's the way ahead in the future.
Okay, thank you. Michael?
A number of the items have been touched on with the challenges for hydrogen as commercial aviation. The availability of the hydrogen, although it can be only about 1% of hydrogen is developed via green sources today, 4 or 5% from gray. A lot of it is coming from petrochemicals, and again, the objective is stop pulling carbon out of the ground. If it's developed via hydrolysis or green sources, so all of that energy has to come from somewhere. It was an interesting study. I think I was looking at the energy demand just for the aviation to support Charles de Gaulle Airport in France was going to need about like 3,000 windmills worth of green energy to satisfy that one airport's jet fuel equivalent energy demand. That's a daunting infrastructure challenge, if you will, for the hydrogen. And then there is the transportation, the storage. The thing that doesn't get a lot of attention is hydrogen is a greenhouse gas. It's a GWP 100 equivalency of 11. It's also about the leakiest molecule on the planet. So the net benefit is, yeah, there's no carbon. However, there is a climate factor that has to be weighted into the total life cycle assessment of its net good. And then when you get to the vehicle, is every study that I've seen worked on, the vehicle is heavier. The hydrogen, the configuration type will vary, the extent of the imposition of the weight and the complexity. Generally, these are LNG requirements for the density of fuel. So although the fuel is light, the vehicle is heavier, more expensive. And then again, as mentioned, there are the layered safety considerations around a hydrogen vehicle. But overall, it's just got a lot of hill to climb to reach, not the feasibility part. I think it's feasible to do a hydrogen-powered airplane. It gets into the practicality, affordability of the fuel, affordability of the aircraft, affordability of the infrastructure, and what is the net total sum benefit depending upon what the alternatives that are being looked at. So far the alternatives seem to be keeping hydrogen at bay. We continue to look at it, but I'll just kind of summarize there.
Thank you. Okay, from hydrogen to SAF, which is a very popular answer to the problems right now. Why does no one talk about how fuel costs are likely to rise as we move to SAF? Won't these fuel costs decrease or lead to lower increases in demand? Why is that not in the projections stated?
As I was saying, as I mentioned earlier, SAF and, we believe SAF is our centerpiece going forward. It is a fundamental, but it's not just SAF. The question is very valid. There are different, as I said earlier, there are different types of SAF depending upon the feedstock and the sources. The HEFAs, which are already starting with a more oily base starting position, are more affordable. Unfortunately, the HEFA-based SAFs are never going to meet the demand for aviation. There'll be 3%, 5%, 6%, 8% type of, I don't doubt they could reach that. So then you have to get into the next layer of SAFs, which are generally, if you're deriving off of different feedstocks, are more expensive to develop, maintain, transport, and get to the aircraft. So there are some scale-up advantages for larger scale, larger plants for SAF. But there are limits to some of those. Some, depending upon the type of SAF you go, it's being dictated by the feedstock, not the size of your refinery and the availability there. So that's what I kind of get back to just summarizing before we move on is how do we find a solution for sustainable fuels that does not stunt aviation demand because it's making aviation too expensive to fly, or it won't be too expensive to fly, but it's too expensive to fly for many. We don't want commercial aviation just to be for those who can afford it. The question is very appropriate. The economics, and not just the cost, but the availability of SAF is daunting, because different parts of the world, we design to a world market. So Brazil may have lots of feedstocks. Australia and different places may not have much bio feedstock and may have to have different blends and arrivals for SAF.
Thank you. Anyone else?
I think it's also a question of the willingness of the oil industry to establish production capabilities for SAF production. Actually, they make a lot of money, honestly speaking, from waste of high-value oil products, because kerosene is nearly waste. So as long as they can sell that, they are not really interested in extending the production capabilities for SAF. On the other hand, I think the basic products to create SAF are also limited. So at the end of the day, the balance will be that for sure the ticket prices will increase because the fuel cost will increase either by the reduction of kerosene availability or by the production of high-value SAF capacities.
Thank you.
Yeah, love the question on SAF because it goes right to the point. We're firm believers in SAF, and it plays a significant role in our path to zero. But it absolutely cannot be the only solution. Right now, we have airlines who are gravitating toward it because, hey, they're looking for a lifeboat, right? And so we're grasping to this life preserver that we don't want to turn out to be an anchor. We need to develop new technologies, whether it's an airframe that uses less energy and will fly further on SAF, or new propulsion technologies, and we're a big fan of what Hulst's doing as well, that give us alternatives, because they're all going to play a significant role.
Thank you. Ben?
Yeah, SAF's not going anywhere. All the planes that are going into service today will hopefully be on SAF in 25 years when we get to 2050. So it's not going anywhere, and I think that as a community, the more we can push for adoption of SAF, and obviously there's a political element to this too. Is Europe is, I think, pushing a little bit harder than the US is right now to bring more SAF into use. That's obviously going to help us get to net zero as well.
Okay. Thank you very much. There are 15 more questions to go, and we have 3 minutes, okay? So let's squeeze in one more lightning round. From gate to runway and vice versa, these are all sources of inefficiencies. A concept exists to move an airplane using an electric power system that will alleviate using jet engines for taxiing. Any thoughts on using this mode to taxi in and out?
Sure. Just really briefly, in our 3 minutes. So e-taxi concepts have been out there. We've looked at e-taxis. And the means is how do you get from the gate to the airport? Where do you already go? You got to fire up your engines at some point, get them saturated, get the thermally set. There's single engine taxi. It's a common practice at some. Instead of firing up both engines, kind of wait to the second one. The energy, the propulsion of the E-systems, they typically carry weight, OEW. The moment you're off the ground, that battery and electric system is hurting your fuel burn. So you're trading ground fuel taxi time or fuel reduction for fuel inefficiency in the air. Typically, those approaches don't factor that if my gross weight's set and my empty weight's higher because of an e-taxi, that's less payload I can get off the ground. And we don't always fly at full payload, but that's part of the practicality or value proposition. So it is an interesting area. There is a lot of fuel burned on that operations on that taxi out, but you have to look at the whole vehicle life cycle impact and value proposition.
Very good. Anyone else?
I think we'll see more of that kind of technology in the next decades. I know that there's work going on to, for example, idle or turn off one of the jets on the taxiway and then turn it on right before takeoff. I know there's other work. Obviously, as electric systems get smaller and smaller and batteries get smaller, makes it easier to install systems like this. So I think we'll see more of this in the next 10 years.
Well, thank you, panel, for giving us your time today out of your busy schedule, and thank you, audience, for attending this session this morning. As a token of appreciation, AIAA will give you each a medallion. So this is a good indication. If you want to get one of those, you got to get up here, and we will be advertising that. So thank you all. This is the end of this session.